Okay, we're going to do a lamina that consists of a plane in the first octave. So to get the plane in the first octave, we get the z-intercept. Okay, z-intercept happens when x and y are both 0. Z is going to equal negative c, so c had better be less than 0, not greater than 0. Okay, so here is zero, zero, negative c. If c was greater than 0, you wouldn't have an intersection with the first octave. Okay. If y and z are 0, then x equals negative a over c, c over a. So you're going to have here negative c over a, 0, 0. Then if x and z are 0, then y is negative c over b, so you have the point 0, negative c over b, 0. And then your region is just this triangular region. So now it's a lamina, we're going to have a density function, but let's just get the surface area of this region. Parameterization is very straightforward. X equals x, y equals y, and z equals negative ax minus by minus c. Say our vector is xi plus yj plus zk. Now you have limits on your x and y. Down here in the xy plane, you just have ax plus by equals negative c, so that y equals negative a over b x minus c over b. So now the parameterization, x can go from 0 to negative c over a. Not remembering that c is less than 0. Might have been more elegant if I'd have just used a minus c here. Okay. And then c could have been greater than 0, it would look a little better, but I did what I did, so we're going to live with it. And then y is going to go from 0 to negative a over b x minus c over b. In other words, this region is described by letting x go from here to here, and then y going from here to here. And it's just a plane region with a straight line, very standard breakdown there. Okay, so here's our parameterization, here's our r vector. So that Tx equals Rx, which is I, and Z is minus AK. Ty equals Ry, which is J minus BK. So the Tx cross Ty equals, just by distributive law, I cross with J gives us K, and I cross K gives us negative J, and K cross J is negative I. So it's this, magnitude of Tx cross Ty equals square root of a squared plus b squared plus 1. This is constant. A and b are constants. I mentioned that you have a normal vector which is believe this, and you can just read off the normal vector very easily. And magnitude of that normal vector is this. The normal vector makes some angle with the xy plane. So if you look at this plane from the side, you've got the normal vector here, the ratio of this hypotenuse to this segment here is a ratio of any area increment on the plane to the region in the xy plane to which that projects. And that's kind of an important thing, but I don't have time to develop it completely, but it comes out completely consistent with what you have here. Okay, and you can explore that for different values of A and B. What's that make the plane look like? What's that make this multiplier look like? Because now you know that the area of our lamina is then the integral as y goes from 0 to negative a over bx minus c over b. And these are just numbers. If you have numbers here for a, b, and c, just do a little division and you just get numbers here. They just got to be numbers. You don't have to worry too much about them. And then from 0 to negative c over a here of this multiplier dy dx this is constant, so it just comes out of here. Now this integral that you're left is just the area integral of this triangle down in the xy plane, which has dimensions negative c over a by negative c over b. And that area is c squared over ab. Because just, multiply the base by the altitude, you get c squared over ab, and take half of that, and you have the area of the triangle, and that's what you get if you do the integral. Now you don't want to necessarily do that integral with all the symbols, but if you do it with numbers, it's always going to come out that way. Now, that's not what we're actually wanting to calculate here. What we're wanting to calculate takes a little more work. It's the mass of the surface, or density, and they use the Greek letter xi, which just kind of corresponds to x, which I think is a little I don't know, maybe it's poetic, maybe it's not. Well, I use the Greek x equals x, and I'll usually use a delta for or a lambda for an area density. But okay, we're going to use the same symbol the book uses, doesn't matter. You want to find the mass. Well, if you think about what happens in a typical increment of the parameter space, mapping to a typical increment here, and incidentally, your parameter space is this triangle. Okay? Parameter space is your triangle in the xy plane. This is your multiplier, consistent with what I at least alluded to here. And so this is just a factor by which you multiply an area in the plane, the area of a region in the plane, to get the area of the region above the xy plane on this plane. Okay, well, you want to find the mass. So if you consider a typical area increment in your parameter space, which corresponds to plane in the real space actually, you're going to multiply the area of that region by the density. Well, this is the area of the region. You multiply it by the density. You're going to get this. You're going to get this. That's a very simple integral. You're going to have an x squared over 2. It's not going to impact the integral of dy, which is just going to give you this minus this, of course, but this is 0. Just going to give you this expression. And then you're going to have an x squared over 2. And x just goes up to some number, so you're going to square that number, divide by 2, you're going to get the result. Okay, so that's in general how you deal with a plane. Now, the details can be different for different planes, but that's really the procedure. And this is general. You could actually take this as a formula and just, bypass the whole process of writing out your parameterization and stuff, but you don't want to do that. You want to learn how to do these parameterizations.